Okay, guys. What we are about to do is the hardest computational thing you will ever do in this class, and maybe the hardest thing you've ever done computationally ever. Luckily, you've got a good teacher. So, guys, in addition to that page that I gave you, which is simply my effort to keep you from having to write down everything, guys, you're going to need another sheet of paper. What we're going to do today is we are going to talk about how weak acids and weak bases respond to titration. So up until now, we've talked about building buffers. We've talked about titrating buffers. We've talked about titrating strong acids and bases with strong bases and acids. Guys, today what we're going to do is we are going to talk about how do weak acids and bases, and specifically we'll start with acids, how do they respond to titration? Guys, what you're going to see is that it's really interesting. So think about what we talked about with buffers. When we talked about titrating buffers, we talked about this I-race box structure, right? Don't just let that be words. Think about that. We talked about this I-race structure, and we said we've got an ice box, which is the weak equilibrium. We attack that weak equilibrium with a strong other. So if it's acetic acid, it's a strong base like sodium hydroxide. And initially in the I-race box, we've got the I and the R and then the A, which is the strong neutralization chemistry that we study in moles. Then we reestablish molarities. That's the A for adjusted molarities. And then that falls to equilibrium just like an icebox, right? Okay. Then, guys, today in homework, we talked about these strong titrations. And we said something really interesting happens in a strong titration. Don't write this down. But, guys, we said something really interesting happens in a strong titration at equivalence. So when we are at equivalence in a strong titration, how much of these do we have left? None. That's equivalence. Guys, if we are titrating HCl with NaOH, as we add the one to the other, when we hit equivalence, all the HCl's been neutralized. All of this is gone. All we have left is this. And what does Na or Cl ion do to water? Nothing. They are the children of the strong acids and bases. This does no chemistry with water, and consequently the pH is 7. Is that all okay? Okay, so guys, what we're going to do today is we're going to bring those ideas together. We're going to talk about this interesting set of chemistries where we are now adding a strong, in this case, base to a weak acid, and it's going to be a blending together of everything that we've learned up until now. Yeah?
So last time we did strong, this time we're doing strong, weak.
Correct.
We're not going to do weak.
No, because understand that's the related rate stuff, right? If you were to add a weak base to a weak acid, you have two competing equilibria that then become intertwined with each other, interestingly around the idea that H times OH is KW. That's the bridge that allows you to do the related rates. But no, we collectively don't know enough calculus to do that, so we won't. Okay, but guys, this is going to be a bringing together of both. So when we say a bringing together of both, let's start with where we started. Guys, this is going to be wildly familiar to you because the lab that we did, and Jeanette, we shared the graphs with you. Guys, the lab that we did works crazy well. So guys, looking at this graph, you'll notice at the top, this is familiar, it is a strong titration. But guys, if this didn't say strong titration, what evidences do you see that this is a strong titration? Yeah, one, the equivalence point is at 7. Wow. Nailed that. Guys, one is the equivalence point is at 7. I see 2 more, maybe more. What are other evidences? Yeah, it starts at a really low pH. It is crazy hard to get a weak acid all the way down to pH 1. Do we need to talk more about that? Okay. I see another one. Maybe. And you're right, it tells us that it's NaOH. What else about the curve would indicate that this is a strong titration? Yeah, but not only does it get, but weak titrations get super steep as well, right? But what about the super steep section? It's relatively long. Guys, in a strong titration, this run-up to equivalence tends to be a huge change in pH. It tends to go from low to high through a broad range of pH change. Yeah.
Isn't there more on the first section below? Isn't it when it's the weak one?
Let's do it. Guys, what I want to do, and again, that I hope you appreciate how good that last lab was. Because guys, what we can do now is we can actually take these graphs and superimpose them. This is what Nathan tried to do, but it didn't work by collecting. Oh, what? No, you're right. Actually, it did work, didn't it? Just you couldn't do the derivatives. Never mind. What I meant to say was this is what Nathan did with great success. But I would never reward you for that because, never mind. Okay. That's right. So guys, look at what happens here. Our green guy is now our weak acid curve, acetic acid. So look at the differences. Guys, let's sort of work from left to right. What do you notice here about the weak titration? Starts at a higher pH, which makes sense, right? It's a weak, understand begging equal molarities, but in general, the pH starts at a higher point. Now, guys, notice this. I'm just going to say it, but I don't want to dig into it a lot. Luke, I think you and I talked about this earlier. Guys, you'll notice that in the strong titration, this slope is relatively constant. But in a weak titration, if we were to just approximate the slope, derivatives, right? If we were to approximate the slope down here, drawing the tangent line, guys, the initial slope, therefore the change in pH, the initial slope is bonkers fast, and then it slows down. And didn't we talk about this, Luke? Guys, I know you're curious, and let's talk about it. I don't want to do a deep dive, but guys, the reason that that is taking place is initially adding a strong base to a weak acid so just ravages the equilibrium and the pH jumps up very quickly. But then that effect starts to lessen. The reason is because it's buffering itself. I'll show you the chemistry quickly, but we're not going to do a super deep dive on this. Let me do it down here. Guys, what's happening is this. This is going to seem wildly familiar. Oh, that was minus. Sorry, minus and H plus. Guys, that's the weak base, or the weak acid, right? We add hydroxide to this. Which direction does it drive the equilibrium? Which way does it go? This way? What happens to the amount of this? Goes down. What happens to the amount of that? Goes up. We're making a buffer. Just like we talked about in lab last time, right? When we get to that half titration point, we've got equal amounts of this and that. We've made a buffer. Does that make sense? We just came at a buffer from a different angle. Instead of making a buffer by adding a conjugate ion salt, we made a buffer by turning half of this into that. Guys, that's actually what's going on right there. This system is actually self-buffering. And as it self-buffers, you see that the change in pH actually happens at a slower rate because it's self-buffering. If that makes sense, great. If it doesn't, don't get hung up on it. But that's what's going on. Then, guys, notice this. These tend to be, this is a little steeper because it's weak, but the rates start to approximate each other. But then, guys, notice this. When this thing starts to approach equivalence, you'll notice, first of all, that it's a higher pH. But as a result, the pH jump that it goes through as it runs through equivalence is much smaller. In this strong titration, it basically goes from like 3 up to, now we'll go back here, about 3 to 11. In the weak titration, it goes from about 7 up to 11. And so, guys, the change in pH is much smaller. But then you'll also notice this, because what happens after equivalence? They're the same. Why would that be true? Because it's a strong base. And guys, at equivalence, what's inside the solution? Salt water, right? In the case of a strong acid-base titration, that salt doesn't react with water and the pH is 7. In the case of a weak titration, one of the ions in the salt is reactive towards water. Therefore, the pH isn't 7. But in either case, it's still salt water. And as you're adding base to the salt water, the pH just climbs as if the salt wasn't even there, even if the salt is partially reactive towards water. You get the idea? Okay. So guys, with all of this said, let's do this. Guys, going back, grab that sheet of paper that I gave you. Guys, going back to this, we have got, I'm going to turn the lights on. Guys, going back to this paper, we've got 1, 2, 3, 4 regions, right? We have got to be able to mathematically calculate the pH in each of those regions. So guys, grab my magic decoder, and you'll notice that on the left-hand side at the top, it says strong acid base. So these are the strong titrations. This is the homework that we graded today. So guys, you'll notice also that we have the 4 regions: initial, before equivalence, at equivalence, and at equivalence, and after equivalence. So guys, how do we find in a strong titration, how do we find the pH initially? It's just the negative log of the molarity, right? That's what this says here. Equal to the concentration of the original solution. It's the negative log of the molarity. Is that okay? Okay. Then guys, before equivalence, the pH is equal to the concentration of the unreacted ion. We find that by subtracting, and don't forget to keep track of volume changes. That's the homework you just graded, right? Do you see how I summarize that? Does it make sense how I said it? Okay. Then guys, what's the pH at equivalence? It's 7, right? In this particular example, if we're doing NaOH and HCl, our product is really salt and water. The salt is not reactive towards the water. It's pH 7. Then guys, look at after equivalence. Does it make sense that it's the same as before equivalence? But now the difference is the unreacted ion that you have is from the titrant and not the thing that you're titrating. Does that sit okay in your brains? Okay. So guys, this is a handy dandy little summary sheet of what you learned last time. Okay? You okay? Questions, thoughts? Are we good? Okay. So now guys, slide that dude to the side. And let's have the same conversation about this graph. Guys, same conversation, but now we're on the green line. So we still have initial, before equivalence, at equivalence, and after equivalence. Do not look at the paper I gave you. Let's talk and then summarize. So guys, let's say that we're taking CH3COOH. I'm going to do it this way. And we're neutralizing that dude. Guys, so you get the idea. The acid is the thing we're titrating, right? It's the stuff in the beaker. So how do we find the pH initially of acetic acid? Icebox, right? This requires an icebox. Does that make sense? Okay. Now, guys, what about before equivalence? Join me at the balanced equation. So, guys, we've got some amount of acetic acid initially. What does the sodium hydroxide do to that acetic acid? Kills it, neutralizes it. How much does it kill? 1-to-1 ratio. Guys, every one of these that we add, one of these dies. So what then determines the pH of the solution? How much of this is left unkilled going to equilibrium? Does that make sense? How do we represent those thoughts mathematically? I-race box. Good? Now, guys, this is the hard one. At equivalence, what's in the beaker? Just the stuff on the right. At equivalence, this is gone, right? What's in the beaker? Salt, water. But in this case, the salt is sodium acetate. What does sodium do to water? Nothing. Sodium is the child of the strong base, sodium hydroxide. It don't do no chemistry. So guys, what determines the pH at equivalence? The acetate ion attacking water. So guys, at equivalence, the pH is determined by the conjugate salt chemistry. Does that make sense? Okay, so this is the conjugate salt reacting with water chemistry. And then, guys, what about after equivalence? The same as in a strong titration. How many moles of this did you start with? How many moles of that did you add? Which one will be bigger past equivalence? The amount of acid or the amount of base? Amount of base. Subtract, convert to molarity, negative log gives you POH, and then go from there. You get the idea? Now grab the paper. Equilibrium acid-base titrations, weak. That's the bottom. Initially, guys, join me at the board. Initially, we said icebox, right? Notice how I said this. Equal to the ion concentration of the original equilibrium solution, icebox. Good? Now, what about before equivalence? Here's how I said it. Equal to the ion concentration of the unreacted particle after it is allowed to reach an adjusted equilibrium. This is an I-race box, and remember to keep track of volume changes. Is that okay? Now, guys, what about adequate? Hydrolysis, hydrolysis, the breaking apart of water. It is not 7 due to the hydrolysis of water by the resulting salt ions. This can then be calculated using a Ka or a Kb of the conjugate ion in an icebox. Okay? And then, guys, notice after equilibrium, if you look up and down, do you notice those are the same? Do you understand why? We okay? Okay. So, guys, we're actually going to do this now. We're going to do this math. This is what we're doing for the rest of the day. Let me switch slides. Bump. We don't need to do that. Okay, here we go. So guys, all we're gonna do for the rest of the day is do the math. So it goes like this. It says calculate the pH of a solution. And guys, I want to do these with you. But it says calculate the pH of a solution that is formed when 45 milliliters of 0.1 molar sodium hydroxide is added to 50 milliliters of 0.1 molar acetic acid. Now guys, if I may, here's our weak acid titration curve, right? You guys writing this down? I'll wait. We got nothing but time. Okay? So guys, let's put this in context. First of all, notice this. The molarities are the same. That's important. But you'll notice the question that we didn't get asked first. The question didn't ask, what is the pH of the untitrated acetic acid? But guys, they could ask us that, right? I think, is it 4.74? I don't know. Do you remember? I think that's actually it. But do you remember, how would we do that? If they wanted us to figure out the pH of the untitrated acetic acid, what would that look like? Do you want to do it? No? No. But what would it look like? We'd have an ice box. Can you picture it? So guys, we've got 50 milliliters of our acetic acid. In order to find the pH of that acetic acid, do we need the volume? No. We just get the sense. You getting it? Right? That almost hurt. You guys good? You're okay? Okay, it's just an ice box, y'all. You did these last test. All we need is an ice box. Ka is equal to products, and then the minus x factors out. We okay? Okay. That's not what we're doing here. Glad we talked about that, though. Okay, so guys, what we're doing here, let's situate ourselves. So we've got, that just keeps getting worse. Same molarities. Good heavens. That's almost embarrassing. Guys, where are we relative to equivalence? We're not initial. Are we before, at, or after equivalence in this question? How do you know before? Just a second, Mark. Or are you just stretching? Okay. So how do we know? Are we before, at, or after? Before. How do we know? Molarities are equal, and we've added less base than we have acid. Is that okay? Okay, so guys, let's then talk about the chemistry, and then we're going to talk about how we're going to approach this. So guys, as we're doing this, and I would encourage you not to write this down, but let's talk about the chemistry. So guys, we've said this before, the chemistry looks like this, and then we've got water. Now, in this particular problem, do we have more acetic acid particles or more sodium hydroxide particles? More. Okay, hold on. We've got equal molarities. We've got 50 milliliters of acetic acid. We've got 45 milliliters of NaOH. Which do we have more of? Acetic acid, right? So when we add this to that, all of the base is going to consume the acid that it can, and then we're going to have a little bit of acetic acid that hasn't been consumed, and then that goes to equilibrium. Erase box, right? Okay, then let's set it up. Sounds like you understand the chemistry, so let's do the math. So guys, in order to do this, we've agreed we're going to solve this. Where did I skip the space? It's after the R, right? Okay. Okay. So guys, beginning to plug this in, we need to do a side calculation. You need to show this where we go 45 milliliters, 1,000 milliliters is 1 liter. 1 liter is 0.100 moles of NaOH. That is not an inconvenience. That's critical. So 0.0045. So 0.0045 moles. So then this is 0.0. Oh, did I do that wrong? Oh gosh, thank you. Yeah, no. Whoa, whoo. That doesn't go there. Yeah, guys, sorry. So we need the acetic acid, and that would be 0.005. Is that okay? Thank you. So 0.005. All right, we'll put it in moles. Is that right? Sorry. And you guys understand that we would need to do that calculation as well? Okay. So then, guys, this is 0, and this is 0. And then, for me, it helps to really make this stand out. So we're then going to add hydroxide to this. Because this is the thing I love about this I-race structure, is that you never have to guess about what's going up and down. So we're adding hydroxide, which drives the equilibrium to the right. So we're doing this. And so then that means that our acetic acid is going to go down and our acetate will go up by the amount of hydroxide that we're adding. That's the 0.0045. So this is minus 0.0045. This is plus 0.0045. And interestingly, proton still hasn't changed. So then we get 0.0005. Is that too many? No, 5 moles. And I'll just do this now. That's divided by 0.095 liters. And then here, guys, we've got 0.0045 divided also by 0.095, and this is still 0. Then we have 0.0005 divided by 0.095 is 0.0053 molar. And 0.047 molar and 0. Then, guys, following from there, minus x plus x plus x. So we have 0.0053 minus x, 0.047 plus x, and x. At this point, it would probably be wildly unsatisfying to not finish this, right? I know. All right, so I'm going to do it over here. Ka is equal to, if we're going to do it, let's do it right. Now I'm curious too. 1.8 times 10 to the negative fifth is equal to 0.047 plus x times x divided by 0.0053 minus x, then that's approximately equal to 0.047 x divided by 0.053. 0053. Whoa. All right, so we've got 1.8 times 10 to the negative fifth times 0.0053 divided by 0.047. Can I just take the negative log of that now, please? Guys, I get 5.7. Is that right? And you understand what we did. You're not going to cut these corners. pH is equal to negative log hydrogen ion. Do that, yeah. Okay. So 5.7 would be the pH. Is that okay? Are we good? You're good? Okay. Have you guys ever taken a second and sort of stood back from this as you're working on this homework and ask yourself, how on stinking earth do I know what I'm doing? Oh, yeah. Yeah, that's right. You guys are doing impressive calculations. You can take pride in that. Are we good? Okay. Guys, this is about to get crazy. Calculate the pH at equivalence. Guys, this is hard. We're going to go slow. All you need to write down, I think, is pH at equivalence. Now, guys, let's talk about it conceptually, and then we can start to play with it mathematically. So if you just write down, calculate the pH at equivalence. Guys, the idea here is that it's relative to the first problem. So you've got the concentrations, you've got the volumes. So this then is the idea. Guys, what we're trying to do, and I think you understand this, but let's be clear. Guys, what we're trying to do is we're trying to find this point in this weak titration. Now, let's make sure we understand why this is not 7. What is the chemistry that is causing that equivalence pH to not be 7, assuming that this is acetic acid and sodium hydroxide? Which ion is reacting with the water? The acetate ion. So guys, this acetate ion is attacking the water. So guys, and is that okay? Do we all share that same common foundation? So guys, if we're okay with that idea, what you need to understand then, and this is surprising perhaps, what you need to understand is back here. Because what you need to understand is that we are never, please don't write this down, we're never going to icebox this to figure this out. This chemistry, this thought, this calculation has nothing to do with this. This is not the chemistry that determines the pH at equivalence. So guys, let's back out of this then and figure out the chemistry that does apply at equivalence. So to do that, we've got to look at the entire system. So as this chemistry takes place, as we're adding base to the acid, what are our products? Sodium acetate and water. But I'm going to write the sodium acetate as it actually exists in the beaker as ions. Now, Guys, if we could picture, and I don't want to draw the beaker, which I know, I'm fighting the urge. Guys, if we were to draw the beaker, I almost have to now. Which of these things is actually in the beaker? Do we have any of this in the beaker? No. Do we have any of that? Thank you. At equivalence. Do we have any of this in the beaker? It's gone too. That means this is the correct arrow because the sodium hydroxide is a strong titrant. So guys, in the beaker, that's what we've got. We've got water, and we've got sodium ions, and we've got acetate ions. Now, does sodium do chemistry with water? No. It's the child of the strong base. It's a negligible acid. This is gone. Guys, what's left is then the chemistry that we need to study at equilibrium. Does that make sense? Okay. So guys, and this is where we need to start then. This is our ice box. So let's do it. Yeah, I've got room. That's our ice box. So guys, I'm going to move it over a little. So guys, what are our products? There's our ice box. But guys, understand, and we should talk about this. Are you guys all caught up? Can I make this go away for a second? Guys, going back to where this came from, this is an ice box. It is not an iRace box. The chemistry that we want to study is this simple equilibrium. And as a result, it is fully represented. Where'd it go? Guys, it's fully represented there. So the trick is, what numbers satisfy the ice box? And guys, this is where this gets hard. We're going to end up doing a bunch of side calculations. Now guys, setting up the ice box for a weak base. What is the surprisingly satisfying first thing we get to do? Squiggle out the water. Because water does not have a molarity. Now guys, in order to satisfy this thing, do we need molarities or do we need numbers of moles? Molarities, because this is an ice box, right? So let's do this. Initially, these concentrations are 0. Here's the hard bit. What is the molarity of the acetate ion? And it is not 0.1 molar. So guys, in order to understand the molarity of the acetate ion, we've got to go back and look at the chemistry and figure out where the acetate ion came from. And the acetate ion was created by the titration. So guys, what we've got to do is figure out from this particular titration, how much acetate ion will we make? So turn it to you as a question. How much acetate ion will we make? The same as what? The amount of acetate ion that we killed. Or I'm sorry, acetic acid that we killed. Sorry, I'm hiccuping. Let's say that again. How much acetate ion do we make? The same as the amount of acetic acid that we killed. Does that make sense? But guys, at equivalence, isn't that also the same as this? It is. But it's just get consistent with this. Just start here. So guys, the logic, if you're not following, is this. We need to know how much of this we've got. But we made it. We made it by titrating. So how do we know how much of that we've got? How much of this did we neutralize? So that's a calculation we can do. Because at equivalence, we've got equal molar amounts. So guys, we have 50 milliliters of 0.1 molar. So we go, and haven't we already done this? Yeah. Let's just make sure you're clear. 1,000 milliliters is 1 liter. 1 liter is 0.1 moles of CH3, COOH. So what does that work out to? 0.005? Is it 2 zeros? 5 moles. So guys, tell me about why we can't go plug that number into the icebox. It's not a molarity. So now we need to convert this dude into a molarity. So we go molarity is moles divided by liters is equal to 0.0050 moles. What's our volume? 100 milliliters. 50 plus 50. 0.1 liters. That moves it in the other direction, right? So it's 0.05 molar. Is that correct? Doesn't dividing by 0.1 make it 10 bigger? So it's 0.05 molar. Okay, so now moving this way, we now know this. This is 0.05 molar. Questions about where that came from? You guys okay? Okay, now this starts to feel familiar. Minus x, plus x, plus x. So we have 0.05. We have 0.05 minus x. We have x, and we have x. So guys, I'm going to continue. I'll do it down below. So now we need to write our KB. So we go KB is equal to, would you guys have remembered KB and not KA? Promise? Okay. So CH3, COOH, OH, and CH3, COO. Products divided by reactants. But now, guys, as we continue, for me to the right, maybe for you down, we need values to plug in here. And guys, we got to know KB, but they ain't gave it to us, and they ain't gonna give it to us. But we have Ka. We have the Ka of the parent acid. And if we know the Ka of the parent acid, we can figure out the Kb of the conjugate base by going Ka times Kb is equal to Kw, or 1.8 times 10 to the negative fifth times Kb is 1 times 10 to the negative 14th. Yes, you also need to show that work. You know what? It's a really good question. Frankly, what I learned to do through my schooling is I would purposefully leave some space I preferred to the right. So I would do my calculations, perhaps shifted a little left on the page, and then sometimes I would even draw a line. And I would reserve some space on the right side of the paper to do those side calculations, like figuring out how many moles of acetate ion, figuring out Kb from Ka. I would just leave sort of a little channel down the right where I could do that work.
So then, when you're doing the equations, you just jump to that answer
Mhm.
and assume
And then bring it over. Yeah.
so they can they'll just know that you did it.
Yeah. They will. Yeah. And so, guys, I'm hoping, can you feed me the number? 5.6 times 10 to the negative 10th. Jeanette, go ahead. No, that would be fine, but not necessary. Did they require that in physics? Okay. And that would be totally fine. In chemistry, you do have to write the equation, but you don't have to reorganize it initially for the variable you're solving for. You're welcome to. Yeah. So let's talk about what you do have to do. Anytime you use an equation, you have to identify it. You have to plug in the values that you're using to solve it. And then you have to, of course, show your answer. Any work in between is unnecessary. You can show as much work as you want, but these are the 3 bits you've got to have. The equation, the setup, including units. In this case, there are none. And then the answer. Go ahead, Mark. Mm-hmm. Absolutely. Yeah, what you couldn't do is skip this all together. You have to write something about the general form. If you want to solve it ahead of time and go KB is KW divided by KA, they'd love you for that, but you don't. But there's got to be something that is the general form of the equation. Okay? And even if the general form of the equation is this, right? So understand, you don't have to write out KB is equal to, how does that go? The general form. A, B, no. B, what is wrong with this? No, we're okay. So HB plus OH over B minus, you don't have to do that. Okay, all right. So with that said, 1.8, no, what was it? 5.6 times 10 to the negative 10th is equal to x squared. Is that just x squared? Yeah. X squared all over 0.05 minus x is approximately equal to x squared divided by 0.05 is then equal to, so 5.6 times 10 to the negative 10th times 0.05, and then square root that dude. I'll just put it in scientific notation. 5.3 times 10 to the negative 6th. Can you confirm that? Is that right? Okay. But guys, understand at this point, we're still at least 2 calculations away from the answer, right? Right, because this number is that number, and that is our OH. So guys, what we end up with then is POH is equal to the negative log of OH is equal to the negative log of 5.3 times 10 to the negative 6th is equal to 5.28, and then pH plus POH is equal to 14, or pH is equal to 14 minus 5.28, and that's 8.72. And that's what I wanted to talk about next. Guys, what is 8.72? And the answer is, I think we may have lost sight of it. Guys, the thing that is 8.72 is the equivalence point. And that lines up with what we see graphically. But notice too, we would have predicted that. And guys, the logic goes like this. Make sure you can do this in your head. We're titrating a weak acid. So the conjugate base is not worthless. So we would expect the solution to be basic, right? And in fact, it was, and we got the number. You guys okay? Yeah.
The opposite's true too. Like if it was.
Absolutely. Yeah. But now, guys, try this on for size. What about this? So guys, what we just did was this. We calculated the pH at equivalence. That was all of this. combined together with this. But guys, the question then quickly becomes, what would the calculation look like after equivalence? The answer is, look at yesterday's homework. You figure out the moles of base, you figure out the moles of acid. Which will be greater? The moles of base. Subtract, divide by the new volume, then that gives you the molarity. Do the POH, convert to pH. You get the idea? Guys, I don't know that you fully appreciate the complexity of the stuff that you guys just learned. This is crazy heady stuff. The chemistry and the concepts and the computational side to this, it's pretty heavy stuff. So guys, we are going to fiddle around with these. This is definitely homework to do with your feet on the floor and the world shut out. Guys, as we're talking about this, I don't know if I should tell you about this, but I will. Guys, there's a theory in learning psychology called context permanence. Have you heard of this? Probably not. There's a theory called context. You will perform better on tasks if you practice that task in the same context that you hope to perform it. So for example, and I hate the New England Patriots, but when the New England Patriots get ready to play Denver, Denver is the loudest stinking football stadium in the NFL. Guys, what Belichick does is in their practice facility, he loads that practice facility up with stereo speakers and he bombards his athletes with deafening fan noise, because he knows that they will perform better if they practice in the same deafening environment that they're about to play in. All right, I'll tell you the other story. One of my roommates in college was actually a pretty serious recreational drug user. And he understood this idea of context permanence and decided that he was going to try to pass sophomore physics stoned. So in his mind, he's thinking, I'm going to go take every physics test that I take after smoking pot. So then in his logical brain, he figured if I'm going to do that, I'd better be high while I'm studying too. That didn't turn out very well. He failed out of school. But guys, why am I telling you this? Guys, the reason that I'm telling you this is because some of you, when you sit down to study, I have your headphones. Some of you, when you sit down to study, this is the first thing you do. Do you get to do this on the AP test? Then why do you do it when you study? Nathan, seriously, listen. Guys, I want you to knock this test out of the park. And there's very good research, so good that NFL teams adhere to this research. Guys, if you can't listen to music when you're taking the test, why do you do it when you study? Because, guys, you're training your brain to need this stimulation in order to think. And in the absence of that stimulation, when you sit down to take the AP test, in an absolutely silent library, you're not going to have that stimulation, and the silence is going to be deafening. Because for the rest of this semester, the rest of this year, I would challenge you to not listen to music when you do your homework. Obviously, the choice is yours, but keep it in mind. So guys, you've got your homework. If I remember correctly, you guys did not have, none of you have eyes, right, from previous things.